All right, now let's move on and add another scenario here, and I'm going to name this scenario. We'll call this BbarMethod. And this is an effective stress analysis, so I'll put ESA there right in the title. And what we're going to do now is a little different, right? I'm going to go to, make sure we're on that one, Analysis, Project Settings. And I'm still going to go to Groundwater, and we're going to do Advanced, but I'm going to keep it at Water Surfaces, right? So no steady state FEA, Water Surfaces, Advanced. And now I'm going to click this Rapid Drawdown button. And we'll get to the Duncan, Wright, and Wong method later, but right now I'm going to do effective stress using BBAR. And so this is a common method in some parts of the world, not all that common in the United States. So I'll click OK. Okay, so you don't see the slope stability and transient seepage or finite element tabs anymore because we're not doing it that way. What we have to do is come here to Boundaries and do Add Water Table, and you'll notice that we also have this one Add Drawdown Line. So we have to specify 2 water tables. And what I'll do is specify the first one starting at 0.7, going to that node. Whoops, picked the wrong point right there. Then over to there. So that's the initial water table, and I'll assign it to all materials. Then I'm going to add the drawdown line, and we're going to draw down the reservoir all the way to the bottom of the reservoir right at that elevation of 4 meters. And I'm approximating the piezometric line just as being a straight line here. In reality, it kind of has a curve and comes around, but this is just to illustrate the procedure. You could probably do a better job drawing that line right there if you wanted to. Okay, and then we'll go material properties. We're going to stick with the 5 kPa and 30 degree failure envelope. And one thing you'll see down here now is the rapid drawdown parameters. So I'm going to click undrained behavior. And so what that means is that when the water draws down, the material is not going to drain, right? So it's going to assign some excess pore pressure based on this BBAR value. And I'm going to put the BBAR is equal to 1. That means any change in vertical total stress is going to be equal to the opposite of the change in pore pressure. No, sorry, it'll be equal to the change in pore pressure. So if the vertical total stress changes by negative 10 kPa, the pore pressure changes by negative 10 kPa, and the effective stress doesn't change. So I'm going to click OK. And now I think we have to do our surfaces, surface options, circular grid search, and auto grid. I'll go ahead and do the calculation. Yep, go ahead and save it. And we only want to calculate the BBAR method, so I'm going to uncheck that one. Oh, and then my surfaces were not the right ones. Let me come in here. Oops. Project settings, and then methods. And we'll just do Spencer here. Okay, and now what we find is the factor of safety is 1.417. All right, if we just had the water table down here, it would be 2.002, but we're predicting that as a result of this drawdown, it's 1.417. This is quite a bit different than what we got from our transient seepage analysis example, right, in the previous one. And that's because we're now modeling the pore pressure in such a way that the undrained behavior is being modeled. So we get this negative pore pressure developing that increases the effective stress and gives us this level of stability. So that's how you do the BBAR method. I wanted to show that this is pretty sensitive to what you pick for BBAR. So let's say that this might be, B bar would be equal to 1 for a fully saturated soil where there's no shear-induced pore pressure. Let's say that it's fully saturated, but you get a little bit of shear-induced extra pore pressure, like the material's contractive. Therefore, the B bar would be slightly less than 1, like maybe 0.9, right? So the negative pore pressure, if you get a reduction in vertical total stress, the negative pore pressure would be a little bit less in amplitude than that because there's going to be some positive pore pressure coming from shear. So I'm going to click OK. And this is kind of arbitrary, right? But anyway, I picked 0.9. And we only want to run this BbarMethod case. And now our factor of safety is down to 1.343. So as we change B bar, it becomes pretty sensitive, right? You can make it lower. Let's go 0.8, see what happens. Save the scenario. We'll just run B bar. And now 1.26. So as we play around with this B bar value, it does have a pretty significant effect on our factor of safety. And as I mentioned in the previous video, it's really hard for us to know what that B bar value is supposed to be, or even whether a constant B bar should be used for an entire slope, because it probably varies spatially quite a bit, since shear-induced excess pore pressure depends on mobilized strain level over consolidation ratio and changes in the major and minor principal total stresses.